Hello everybody, today we are going to be taking a look at the Tower of Hanoi problem once again. Last time we figured out the major recursive approach to solving this problem, where we move each disk, getting it from the source rod to the destination rod, utilizing that auxiliary rod in the middle. And we calculated we not only used recursion to find out the minimum number of moves, but we mainly printed out each individual step so that we could clearly visualize each individual disk moving to its correct position. So now that was a very good solution overall. However, printing out every single move is a little bit um, it it has a inefficient time complexity, mainly because of the fact that since we are recursively calling this function within itself 2 times, that is a 2 to the power of n time complexity solution right there. So if there's n like 3, like if n is equal to 3, 2 to the power of 3 is 7. So you see that as n increases, it exponentially grows. So it's not a very good solution, but it does have the benefit of knowing each individual step being printed out clearly, and that it was overall a fairly good solution. However, what if we want to create the same problem, but we don't care about printing each individual move? What if we just wanted to instead figure out the minimum number of moves? So for example, remember when we ran this code, we got sorry, this is actually we got each individual steps. What if all we wanted was the number of steps? So you see how there are 7 moves here? What if we just wanted to return 7 as the result? And what if we want, for example, if we switch to n is equal to 4 and then run the code here, we see this should be 15, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, so 15 lines there. So what if we wanted to find the minimum number of moves in particular? We could still use the same thing and just have, instead of printing it each out, we would have like a variable in here that would continuously increment, and then we would finally return a single value. However, once again, this is a 2 to the power of n solution. So let's try to find a faster method of doing this using dynamic programming. So in a dynamic programming, we can do this using a bottom-up approach, where we first want to create a DP table. Using let's first create the function tower underscore of Hanoi. Let's call it Hanoi underscore DP. Okay, since we don't need necessarily the source, auxiliary, and destination, since we only needed those statements to create out the printed text, all we need is the number of disks that we need to find, right? So the goal is to find, okay, so if it's 3 disks, we have to return 7 steps. We need to count the number of steps. So how do we do this? Now, if we remember our solution, first we go from the source to the auxiliary, and then we go from then we move the largest disk from the source to the destination, and then we move everything that was previously on our auxiliary to the destination. So that was the overall process. So how do we form it into our dynamic programming solution? So first, let's create our DP table. DP is equal to, we have to initialize this list, and to do that we simply state what size is it. What size do we want? Well, we could do n, But in this case, what we want is an extra slot because we want to start from the table of 1 because that's the most convenient, right? So we could calculate it starting from the first disk 1, and then the second disk we'd use the second index. So because of that, we want to do n plus 1 because obviously 0 disks we could remain at 0 because obviously 0 moves would be correct, but 1, how would we be able to do it? 1 would just be 1, right? So starting off with the base case, we know that the first index dp01 is equal to 1, and this will always be true. Next, we need to loop through the rest of the DP table, calculate the rest of the DP table, and figure out how we could do that here. For I in range of 2 to n plus 1. We need to figure out the method to figure out exactly how many moves it takes to do each disk. So if we see the method, basically we're moving it from the if we think about the recurrence that's happening over here in a recursive function, we're calling this function 2 times, right? So that gives us a hint that it's 2 to the power of n, right? However, one thing we also want to know is that because it's 2 to the power of n, does that mean that it just simply doubles? But not exactly, right? Because as we've seen, this is the n equals to 3 solution. We have 7 moves, and 2 to the power of 3 is not 7, it's 8. 2 to the power of now, and if we take a look at 4, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It's going to be 15, right? But that isn't 2 to the power of 4. That's 2 to the power of 4 minus 1. So you see that minus 1 thing? That's the key to solving this problem right now, right? So what we realize, and it overall makes sense because what we see in our recursive solution is we're moving all the disks from the source to the auxiliary. This is an auxiliary. Going from the source to the auxiliary is one step. Auxiliary to the destination is another step. And because of those two steps, it is basically the these two steps are representative of 2n, but we also have to subtract the fact that we're moving the final disk to the destination, and that's what causes it to be the minus 1. So to represent this, what we would do is we'd take whatever step we are on. So for example, dp of 1 is 1, right? But we want to figure out dp of 2, dp of 3. We could also imagine the dp of 2 situation right here, right? Quickly, obviously this function is incomplete, but what we can say is we could quickly calculate what it would take for dp of 2 to fully get the pattern here, and we see that it's 3 steps, right? And that tracks out 2 to the power of it's not exactly 2, it's 2 to the power of 2 minus 1, right? Or another way of thinking about it is it's actually double the previous one plus 1. So to figure that out, we could say is equal to 2 times the previous value. The previous value in the dp table is indicated by I minus 1, and then you just add 1. So basically that should be the solution, so that we get the dp of 2 is equal to 1 times 2 plus 1. and that's equivalent to 3. And then we do for it would be 6, and then it would go to 7, and then 7 would go to 15, and etc, etc. And there it is, basically. It's represented by these two recursive calls and then the addition of 1. I know I said -1 in the 2 to the power of n minus 1 recurrence, but it's essentially the same thing, because printing it out requires 2 to the power of n minus 1, but when we're actually trying to calculate the total number of moves required, this counts as an additional 1 being added. So there we go, and then we could return out, finally, the entire list of dp of dp. We have our dp table created, and the final value in our dp table, dp of n, well, because it actually has a length of n plus 1, so the last index would just be n, right? And this is what we're returning. So now that is the solution. We could find an example of print, you could say minimum moves. And then we could say Tower of Hanoi DP. And then we have to take in the parameter as n. And this works out perfectly because we have the n here, all n already defined here. So what we have is the specific steps being taken, and then finally the second function that we made with dynamic programming, telling the total number of moves that were just made. So we could run this code, and it says the minimum moves 3, and it'll list it out here. I think technically it would be better to have this first, actually, because whoops, this one here, and now we run this. Whoops, I should have deleted it here. Okay, now here we go. Okay, my bad. I for some reason I forgot to put the value of n, and I have to put n here. I'm speeding through it, so I'm making a couple of mistakes. But here we go. Now we have the minimum moves listed, and then it'll show each individual step to get to that. And that's what we just coded here. The minimum moves thing is what we just coded. Alright, so now we could test it with greater and greater results. If we tested with 3, which was what we started off with, we can see that clearly it takes 7 moves from get to A to C, and then A to B, and then C to B, so on and so forth. And then to get it to 4, it'll tell the exact number. It says minimum moves 15, A to B, A to C, B to C, and then so on and so forth. And if we go to 5, you probably see the pattern here. This one should be 31, and it is 31 because it's double plus 1. And yeah, that's essentially the solution there. Hopefully the logic makes sense on how we figured out the recurrence pattern, the pattern that emerged from this to determine the minimum number of moves needed to solve this problem. And hopefully the logic was pretty clear. That's how we solve it via dynamic programming. Once again, this the recursive time complexity in the initial one was 2 to the power of n minus 1 specifically, or 2 to the power of n, basically, big O of 2 to the power of n. However, the dynamic programming solution is way more efficient. It only uses the additional space complexity of, obviously, space complexity of n creating our dp table, but the actual time complexity itself is a single for loop, so it's a time complexity of n, essentially. So yeah, that's how we solve this problem. Hopefully you guys understood it, and yeah, I'll see you again next time. Bye bye.